Hello. So we're almost done here. We're just going to review for the final exam. So these are the questions from the practice questions from the final exam. I'm just going to skip number 1. That's just a question on vectors. So I'm assuming you all know how to add vectors, subtract vectors, take the dot product, cross product, find the angle between vectors, right? So those are pretty standard. Number 2 is a bit more interesting, right? So we have a 150 Newton crate resting on an inclined plane of 22 degrees. Okay, that's roughly 22 degrees here. And so we have this very heavy crate, 150 newtons. That's pointing straight down. And part A, we're looking for the force exerted normal to the plane. So that's this force here. Yeah, we can call that N for the normal force. And the force of friction exerted on the crate, keeping it at rest. So that's essentially tangents to the plane. So we can call that T if you like. Or F for friction, but so I'll just call it T, right? And what's probably not clear from this is I'm really just looking for the magnitudes of these vectors, right? So when it says force is a vector, but in this case we just want the magnitude of these forces, right? And so this is really just trigonometry. If you take the 150 newtons and then decompose it into these two forces, right? There's the 22-degree angle. Right? So N is just going to be the 150 newtons times the cosine of 22 degrees. And the magnitude of, this is part B already, the magnitude of the tangential force or frictional force is the 150 times the sine of 22 degrees, right? And those are the exact forces, but we can approximate just using our calculators. And so 150 cosine 22 degrees is about 139.08. And this would be in newtons. And then 150 sine of 22 degrees is approximately 56.19 degrees. And I think that's all we're looking for. Right? So yeah, this is really just resolving a vector into its components. Right? So nothing fancy there. Of course, if you want the vectors, you can figure out N as a vector and T as a vector, presumably in terms of I and J. Now, whether you want, I and J to look like this, it might make it easier. But typically, I and J would look like this. And then, it's both N and T will have components in the I and J directions. All right, so moving on to number 3. We have 3 points labeled P, Q, and R, and those are the coordinates. If it's a little small, let me just copy them down. So point P has coordinates 1, 2, 3. Point Q has coordinates 2, 4, 5. And point R has coordinates -1, 3, 5. Of course, we can assume that this is the standard rectangular coordinates x, y, and z. Right, so part A, we're looking for the parametric equations of a line passing through points P and Q, so this has nothing to do with R. And the easiest way to get the components, right, is just to, again, you can do this by using x0, y0, z0. I'm going to assume that those are the coordinates of point P. And then we just need a vector, right? So this is going to be the coordinates 1, 2, and 3. as a vector, plus t times the vector from p to q, right? Or any multiple of that vector, of course. Oh, so I'm sorry. So there should be a vector here. And maybe I shouldn't use x then, although some books do use x for a vector. I'll use r. That's the typical position vector, right? Okay, so back to the vector from p to q. When you just subtract the coordinates, 2 minus 1 is 1, 4 minus 2 is 2, and 5 minus 3 is also 2. So this is really just the vector 1 plus t, 2 plus 2t, and then 3 plus 2t. So there you go. You can leave it as a vector-valued function. Although way back in chapter 11, we didn't have that notion yet. We just wrote them separately like this. So either way is fine with me. Yep. So yep, this is the set of parametric equations for the line passing through the 2 points P and Q. Right. And so for part B, now we want the equation of the plane passing through P, Q, and R. So now we have to include R, of course. And the idea is you have your 3 points. We're assuming that the 3 points are not collinear, right? They don't all lie in the same line. They lie in some plane here, right? So usual thing is, let's say this is P, this is Q, this is R. We can form the vector from P to Q. In fact, we did that already. That's this vector here. And we can either do from Q to R or P to R. I guess I'll do the vector from P to R. And so that's going to be negative 1 minus 1, so negative 2. 3 minus 2 is 1, and 5 minus 3 is 2. Okay, so both PQ and PR, well, I guess I'll write down PQ again, 1, 2, 2. Both of these vectors lie in the plane, but in order to get the equation of the plane, and just to remind you, it should look something like this, where A, B, and C are just the components of a vector normal to the plane, right? Perpendicular to the plane. So easiest way to get that is just take the cross product of PR and PQ, right? I mean, yeah, you can do, PQ, PR, right? Doesn't matter. Although if we do PR, PQ, I guess it will be, an upward. If you do PQ cross PR, it'll be the same vector but pointing downward, right? So you know how to do the cross product, right? You can just do the determinant here. Right? So this is going to be 2 minus 4, which is negative 2, and then 2 plus 4, which is 6, and then negative 4 minus 1, negative 4 minus 1, negative 5. Right? So these are just my components, A, B, and C. And my x0, y0, z0 could be any one of these points. Again, I labeled it as the coordinates of P, so I'll do the same thing, right? So then the equation of the plane will just be A, so negative 2 times x minus x0, x0 is 1, plus 6 times y minus y0, which is 2, and then plus c, so negative 5 times z minus z0, which is 3. And so that equals 0. Again, don't leave it like that, right? You want to multiply it out and put it in the standard form. So negative 2x plus 6y minus 5z. And then what do we have? Plus 2 minus 12 plus 15 equals 0. So negative 2x plus 6y minus 5z. And then this is negative 10 plus 15, so positive 5. And that's good enough. I think, aesthetically unpleasing to have the first term being negative. So if you just multiply by -1, that might make it look a little bit better. But again, it's not required. I'll accept either. Okay, number 4. Find the distance between the point Q with coordinates 5, 2, 0 and the line given parametrically by x equals 3 minus 4t, y equals 1 plus t, and z equals 2t. Okay, so in order to do that, I would just look up at the formula sheet or in your book. Here's the formula for the distance between a point and a line. And that's what we have here. So let's see. Q is the point that's not on the plane, or I'm sorry, on the line, right? Yeah. So right. So we have a line containing a point P in the direction of V. So in fact, that's exactly what we have. And we have let me write it as a vector valued function. So this is just the equation of the line, 3 minus 4t for x, 1 plus t for y, and then 2t for z. Right, so we have the point 3, 1, 0. So that's on the line. That could be our point P then. And then the vector v would just be -4, 1, 2. Right, so that's a vector that lies in the line, or is parallel to the line, essentially, in the direction of the line. Okay, so I think we have all the information we need. Again, Q is the point 5, 2, 0. So what do we need? We need the vector from P to Q, right? You could use the vector from Q to P. It doesn't matter here. So this is going to be 5 minus 3 is 2, 2 minus 1 is 1, and 0 minus 0 is 0. And then the vector v, we got that from the coefficients of t, again, so -4, 1, 2. All right, and we just need the cross product of those. So PQ cross V is going to be the vector 2 minus 0, so 2, and then 0 minus 4, so -4, and 2 plus 4, right, so 6. Okay, now be careful not to scale this, right? Don't just divide by 2 here, right? Because then you're going to get the wrong distance, right? So again, here's the picture. You have a line, so you have some point P, you have a vector V in the direction of the line. Make that a little bit clearer here. And then you have some point Q over here, right? That's not on the line, and we're looking for this distance, right? So we're getting it by the vector from P to Q. So we need that distance, right? So the magnitude of the vector PQ cross V is the next step here. The magnitude or norm is just going to be the square root of 2 squared plus -4 squared plus 6 squared. So I think that's just going to be 4 plus 16 plus 36. So square root of 56. Right? And then we just divide by the magnitude of V itself, which is the square root of, again, -4 squared plus 1 squared plus 2 squared. So we have 16 plus 4 is 20, plus 1 is 21. So, right, so according to the formula, the distance is just going to be the square root of 56 divided by the square root of 21. Right? Or you can just do the square root of 56 over 21. And if you divide top and bottom by 7, I think that just reduces to 8 over 3. Right? So the square root of 8 over 3. And according to my calculator, that's approximately 1.633. Or just 1.63, I guess, is good enough. Right? It doesn't say it around. So again, the square root of 8 over 3 is fine. Or if you insist on rationalizing the denominator, I think we just get the square root of 24 over 3. Right? And you can simplify the square root of 24 as 2 square root of 6 over 3. But as you know, I'm not picky. As long as you write down the exact distance and not just the approximate, the 1.63. All right, number 5. Okay, so you have a particle moving along a curve with components log t for the I component, 2t for the j component, and then t squared for the k component. Again, I'll write it a little bit bigger so you can see it. So natural log of t times I plus 2t times j plus t squared times k. And t has to be bigger than 0. After all, that's the domain of the log function. So yeah, so t has to be positive. All right, so what do we want? We want, in part A, the velocity, speed, and acceleration. So let's just start with the velocity. You know that is the derivative of the position. So that's just going to be 1 over t times I plus 2 times j plus 2t times k. Right? Or if you prefer this notation, you could do t to the negative 1, 2, and then 2t. Either way. So that's the velocity. For the speed, right, v without the vector over it, or better yet, the magnitude of the vector v, that's just going to be the square root of the sum of the squares of the components, right? So 1 over t squared plus 2 squared is 4, plus 2t squared is 4t. And that's kind of a mess with the 1 over t squared. So I think what I would prefer to do here is get a common denominator, which is t squared. So 1 plus 4t squared plus 4t to the 4th, all over t squared. And I think we can simplify that further. The 1 plus 4t squared plus 4t to the 4th, all under the square root. And then the square root of t squared is just t. Again, we're assuming t is positive. But if you notice, everything under the square root here is just a perfect square. I think it's just 1 plus 2t squared squared. So in the end, we're just going to get 1 plus 2t squared over t. Right. Or if you prefer, t to the negative 1 plus 2t. Again, I'm not picky about that, right? So that's the speed. Remember, speed is a scalar, right? So there's no vectors here. Okay. Oh, and then the acceleration is just the second derivative of the position. So take the velocity and just take one more derivative. So we're going to get negative t to the negative 2, 0, and 2. Or if you prefer, negative 1 over t squared times I plus 2 times k. Yeah. Either way. All right, that's part A. Part B, we want the arc length of the path of the particle moving along this curve from t equals 1 to t equals 2. So the formula for arc length, if I remember, I'm going to use S for arc length. It's just the integral from a to b, in this case t equals 1 to t equals 2, of the magnitude of r prime. And you recognize that as the speed. So we already calculated the speed in part A. Here it is. So we just have to integrate from 1 to 2, 1 plus 2t squared over t. And it might be more helpful to write it the second way, right? So 1 over t plus 2t. So integrating that, I think we're all comfortable with that. We just get natural log of absolute value of t plus t squared, and then evaluate it between 1 to 2. It's just the fundamental theorem of calculus, right? And in fact, so we don't need absolute value here because 1 and 2 are positive numbers. So we get log 2 plus 2 squared, and then minus log 1 plus 1 squared. So this is just log 2 plus 4 minus 0 minus 1. So it's just 3 plus log 2. Right. Yeah, again, it's very rare that you can evaluate these arc length exactly. But when the speed, the magnitude of the velocity, is a nice simple function like this, it's not that hard. All right, and part C, the unit tangent vector and unit normal vector at t equals 1. Okay, so for the unit tangent vector, I think you probably remember that as just the velocity, which doesn't have to be a unit vector. So to make it a unit vector, we normalize it. We divide by its magnitude. Right? Yep. And of course, this could be a function of t here. Although we only care about this at t equals 1, right? And so with that, you can, right, if you just want the unit tangent vector at t equals 1, you can just evaluate the velocity and the speed at t equals 1. So what was the velocity? So it was 1 over t plus 1 over ti plus 2j plus 2tk. So if t is 1, we just get I plus 2j plus 2k, or 1, 2, 2. And the magnitude of that is 3. Right? So 1 plus 4 plus 4 is 9. Square root of 9 is 3. So we just get the vector with components 1/3, 2/3, 2/3. Right? Okay, so yeah, that's the easy one. The more difficult one, of course, is the unit normal vector. So remember how that goes. We have to take the derivative of the unit tangent vector and then divide by the magnitude of the derivative of the unit tangent vector, right, to normalize it. Okay, so yeah, here obviously we can't plug in 1 and then take the derivative because we just get 0. So we have to go back to, well, we have to find t as a function of time. So to do that, let's go back to the vector r prime and just normalize it. Yeah, I probably should have done this already. Yeah, so let's start with r prime as a function of t. Right, it was just the vector 1 over t, 2, and then 2t, just making sure. Okay, and so now we just divide by the magnitude, or the norm, which was just, yeah, 1 plus 2t squared over t. Okay, quite a mess. But this is just, let's see, 1 over t times the reciprocal t over 1 plus 2t squared. And then this will be 2t over 1 plus 2t squared. And then this will be 2t squared over 1 plus 2t squared. So, right, so 1 over 1 plus 2t squared. And then 2t over 1 plus 2t squared, and then 2t squared over 1 plus 2t squared. Right, and you can now check that this is a unit vector. So this is the unit tangent vector as a function of time. Okay, and of course now if you plug in t equals 1, you just get this again, the 1/3, 2/3, 2/3, right? Okay, but now we have to take the derivative of this, and That's harking all the way back to Calc 1. So we have your quotient rule here. So denominator times the derivative of the numerator, which is 0, minus numerator times the derivative of the denominator, all over the denominator squared. And then do the same for the second component. Now it's going to be a bit more complicated. So denominator, derivative of the numerator, minus numerator times the derivative of the denominator, again, over the same denominator squared. And for the third component, again, denominator times the derivative of the numerator, minus numerator, derivative of the denominator. Okay. Again, good review of Calc 1 and quotient rule and all that. I dare say we should probably simplify this a bit. So, in fact, let's sort of just factor out the denominator here, leaving us with the numerator of negative 4t. So this up here is going to be 2 plus 4t squared minus 8t squared. So that's just 2 minus 4t squared. And then here we're going to get 4t plus 8t cubed minus 8t cubed. So that's just 4t. And there you have it. And maybe I should write this all as one vector here. Although I guess we don't have to. So we just have to take the magnitude of all this and then divide by that magnitude. Same denominator. All right, I'm getting lazy here. Okay, so what's the magnitude of this vector? Okay, so rather than do that, because remember, we only care about this when t is 1. Sorry, when time is 1. Oops, prime. So let's just plug in 1 here to t prime. So what we get for the numerator here, we get negative 4 divided by 3 squared is 9. So all the denominators will be 9s then. Gosh, I can't write a 9. There we go. And then 2 minus 4, so negative 2 over 9. And then 4 over 9. Okay. Yes, so that's not a unit vector. I don't believe it is. If we take its magnitude, we get the square root of 16 over 81 plus 4 over 81 plus 16 over 81. So that's 32 plus 4 is 36 over 81. Under the square root, that's just 6 over 9, or 2/3. So after all that, we just divide by 2/3 or multiply by 3 over 2. Oops, sorry, vector. So it looks like we just get negative 2 over 3, negative 1 over 3, and then 2 over 3. All right. So yeah, a bit of a nuisance to calculate the unit normal vector. This is the principal unit normal vector, of course. Yep. And one way to check fairly quickly that this at least is reasonable is if we take the dot product with t of 1. So just to remind you what t of 1 was, the unit tangent vector at 1. Right, it was, yeah, 1/3, 2/3, 2/3. So the dot product of t and n is just going to be, let's see, negative 2 over 9, minus 2 over 9, plus 4 over 9, which is indeed 0. So, right, that's the whole idea here, that if this is the curve, right, this would be the tangent vector, this would be a normal vector. They have to be orthogonal, so the dot product has to be 0. Okay. Again, that doesn't mean it's correct, it just means that it's reasonable. Okay, so number 6, we have w is a function of x, y, and z, and x, y, and z are functions of both s and t, and we want to find the two partial derivatives, the partial of w with respect to s and the partial of w with respect to t. Right, so that's just the chain rule, which I just wrote down here. So let's just see what we get. So in this case, w is just the natural log of x squared plus y squared plus z squared. Right? So the partial of w with respect to x is just going to be, well, 1 over x squared plus y squared plus z squared times the derivative, which is just 2x. Right. And similarly, the y partial of w is just 2y. And again, if these symbols here, if you're thinking these are 2's, guess again, those are partial derivative symbols. I know they look a lot like 2's, so be careful of that. Then there should be a 2y. Right. And then the partial of w with respect to z is going to be 2 times z over the same x squared plus y squared plus z squared. Right. And I forgot to write down what x, y, and z are. X is just sine of s times t, y is cosine of s times t, and z is s squared plus t squared. Right. So what we probably should have done, but better late than never, is to take x squared plus y squared plus z squared and write that in terms of s and t. So it's going to be sine squared of st plus cosine squared of st plus z squared is going to be s to the 4th t to the 4th. And Pythagorean identity, this is just 1 plus s to the 4th t to the 4th. And so, right, that's what the denominators are going to be. Right? And in fact, w is just the natural log of that. So at this stage, we don't even need the, 4 and 4. At this stage, we don't need the chain rule for partial derivatives. We just use the ordinary chain rule from Calc 1, right? So yeah, we could just, right, the quick way of doing this, of course, is just to take the partial derivatives of this with respect to s and t. But again, I think they wanted us to use the chain rule, so we can rewrite each of these in terms of s and t, of course. This is just going to be, 2 sine of s and t, or s times t rather, divided by 1 plus s to the 4th t to the 4th. And then the y partial will be 2 times cosine of st divided by 1 plus s to the 4th t to the 4th. And then the z partial will be 2 times z, which is s squared t squared, over the same 1 plus s to the 4th t to the 4th. Right. So the s partial of w is just going to be, well, the x partial of w, which is just this, copy that down. Times the s partial of x. So if I take the partial derivative of x with respect to s, we're just going to get t times cosine of st. So this will be t times cosine of st plus, and then the y partial of w, which is right up there, times the s partial of y. So it's going to be negative t sine of st right, and then plus the z partial 2s squared t squared over 1 plus s to the 4 t to the 4, and then that times the s partial of z, which is just 2s t squared. Right. So just putting it all together, you're going to get 2 sine times cosine, and then minus, oh, I forgot a t here, 2t sine cosine, minus 2t sine cosine. So that adds up to 0. And then plus 4s cubed t to the 4. Right, and this is all over 1 plus s to the 4 t to the 4. So we're just going to get 4s cubed t to the 4 over 1 plus s to the 4 t to the 4. Right. And just to show you that this would have been really easy if you just did this directly. After all, w is just natural log of 1 plus s to the 4 t to the 4. So the partial of w with respect to s is just going to be 1 over 1 plus s to the 4th t to the 4th times the derivative of s to the 4th t to the 4th, which is 4s cubed t to the 4th. So much faster to do it that way. Right, and so you got to do this all over again for the t partial of w, but I think you can handle that, right? If you can handle the partial derivative with respect to s, it's not much harder to do the partial derivative of w, but with respect to t. In fact, I'll just use the shortcut here. Right, so it's still going to be 1 over 1 plus s to the 4th t to the 4th, and now the derivative of 1 plus s to the 4th t to the 4th with respect to t is 4s to the 4th t cubed. So without going through the whole chain rule up here, we got both answers this way. Right, so much easier to do this directly. And the question didn't exactly say you couldn't do it directly, so either way is fine here. Okay, number 7. Find and classify all critical points of the function f of x, y equals 12x plus 27y minus x cubed minus y cubed. Okay, so critical points are where the partial derivatives are equal to 0 or where they don't exist, but that's not an issue here. So the x partial is just 12 minus 3x squared. So set that equal to 0. And then the y partial is going to be 27 minus 3y squared equals 0. So you get a system of 2 equations and 2 variables, which is really easy to solve, right? X squared is just going to be 12 over 3, which is 4. So we get x is plus or minus 2. And y squared is going to be 27 over 3, which is 9. So y is going to be plus or minus 3. And notice these are all independent, right? So the critical points are going to be where x is positive 2, y is positive 3. X could be negative 2, y could be positive 3. X could be positive 2, y could be negative 3. And then they could both be negative, negative 2, negative 3. So we have a total of 4 critical points. Now, classify them, and what we mean by that is classify them as, relative maximum, relative minimum, or a saddle point. And so remember, for that, we first have to calculate this quantity I call D, which is sometimes referred to as the Hessian matrix, or determinant of the Hessian matrix. So it's just going to be the second partial derivatives fxx times fyy minus the square of fxy. So now we need the second partial derivatives, and that shouldn't be too hard. So I think you just get negative 6x for fxx, fyy. It's going to be negative 6y. And then the mixed partial derivative, if we take the derivative of 1 say, fx with respect to y, we just get 0. So this is really just going to be positive 36xy. Okay, so let's start with 2, 3. So 36 times 2 times 3, or 36 times 6, I think is 108. But that's positive, so we know we're going to have a maximum or minimum. And which one it is, we'll just plug into the second derivative, fxx, for example. So that'll just be negative 6 times 2, which is negative 12. If you remember, a negative second partial derivative means it's concave down, so it means we have a relative maximum, right, at the point 2, 3. Right. So what about negative 2, 3? So here, D is going to be, I guess, negative 108. So we can stop there. We don't need the second partial derivative. This is a saddle point. And I think the same is going to be true for 2, negative 3. If D is negative, you again get another saddle point. And finally, when they're both negative, D is again positive 108. So plugging into the second derivative, negative 2, negative 3, we're just going to get, let's see, negative 6 times negative 2, we're going to get positive 12. And a positive second derivative means it's concave up. So we have a relative minimum at the point negative 2, negative 3. So 2 saddle points, 1 maximum. Right. Yeah, here are the saddle points. I didn't write them down. And then 1 relative minimum at negative 2, negative 3. All right, that's it for number 7. Right, moving right along to number 8. We have the surface z is equal to x times e to the y, and we're looking for the tangent plane at the point 0, 1, 0. Right, so what do we need for a tangent plane? Well, what do we need for any plane? We need the equation of the plane, which we did this earlier, I think. Yeah, there was a problem where we needed the equation of a plane, I seem to remember. So in this case, the normal vector, the a, b, and c, right, we can't get that because we only have just the 1 point, right? We need 3 points to determine a plane. So for a tangent plane, if this is the surface, right, remember we're going to use the gradient vector as our normal vector. So we need to find the gradient of f. All right, so what is f? So here's where you have to be careful, right? F is a function of 3 variables. So it's going to be a level surface. So I'm going to subtract z from both sides. So this is the level surface where x e to the y minus e equals 0. Okay, right, it has to be a function of 3 variables, right? So that when you take the gradient of that, right, you get a vector in space. So this is just going to be e to the y, x e to the y, and then negative 1. So our particular normal vector is just the gradient at the point 0, 1, 0. So e to the 1 is just e. 0 times e to the 1 is 0, and then, well, z is negative 1. The z component is negative 1. Okay, so that's my a, b, and c. And we already have our x0, y0, z0. That was given. That was 0, 1, 0. So, so the equation of the plane is just going to be e times x minus 0 plus 0 times y minus 1 minus 1 times z minus 0, and that equals 0. So we get e times x minus z equals 0. Or if you like, just z equals ex. Either way. Right? So be careful. It's e times x. It's not e to the x, right? So e is just the coefficient of x here. Okay, number 9. We want to find the directional derivative of the function f of x, y, and z is equal to x to the y plus x times the square root of 1 plus z at the point 1, 2, 3 in the direction of the vector 2, 1, negative 2. Okay, so directional derivative, right? I remember that as this notation. It's really just the gradient of f, right, at your specific point, and then take the dot product with u, which is the direction of the vector. Now, we're given the vector v is 2, 1, negative 2. However, that's not a unit vector, right? When you're using this formula, u has to be a unit vector. So let's take the magnitude of v, which is, well, 3, right? So u then is just going to be v divided by 3. So 2/3, 1/3, negative 2/3. Okay, so that's my u. All right, now let's take the gradient of f. So the partial of f with respect to x, right? So here we're treating y as a constant, so this is going to be, right, I'm sorry. We want the whole vector, right? So let's just write it this way, right? f subscript x times I plus f subscript y times j plus f subscript z times k. All right, so first the partial of f with respect to x, right? So that's just going to be y x to the power y minus 1. That's the power rule for derivatives. Plus, and then just the square root of 1 plus z, which I write as 1 plus z to the 1/2, right? So all of that times the vector I. Now with respect to y, now x is a constant, right? So the derivative of x to the y is going to be x to the y times the log of x, right? And then the second term doesn't depend on y, so that's just the derivative of that is 0, so this is times j. And then finally the z component, the partial with respect to z, is going to be 1/2 x times 1 plus z to the negative 1/2. I don't think I'm forgetting anything there, right? Yep. So that's the gradient of f. So now I guess we can just plug in the 1, 2, and 3. So we get a vector, let's see, 2 times 1 to the 2 minus 1. So 2 times 1 is 2, right? Yeah, 1 to the 1. All right. Plus 1 plus 3 to the 1/2. So 1 plus 3 is 4. Square root of 4 is 2. So 2 plus 2 is 4, right? And then the j component, or the y component, will be 1 to the 2 times the natural log of 1, which is just 0. And then the z component, k component, will be 1/2 times 1 times 1 plus 3 to the negative 1/2. So I think we just get 4, 0, and then 1/4. Okay, so that's the gradient, and then we just need the dot product with u. So the directional derivative of the function f in the direction of u is the dot product of 4, 0, 1 over 4 with 2/3, 1/3, negative 2/3. So let's see, we're just going to get 8 over 3 plus 0 minus 2 over 12, which is 1 over 6. Okay, so that's 16 minus 1 is 15 over 6, which reduces to 5 over 2, so 2.5. Okay, moving right on to number 10. There's a couple of double integrals we want to calculate. So let's start with A. This is the definite integral from 0 to 1 of the definite integral from y to 1 of e to the x squared dx dy. Okay, so the question is, can we do this inside integral? And the answer is no. At least I don't know how to do it. Right, this is one of those integrals that's, I'm not even sure it has a name. I know if it's e to the negative x squared, that's just the usual Gaussian, from statistics. But if it's e to the positive x squared, I wouldn't even know where to begin with that. So there's no way to do it directly like this, right? We're going to have to switch the order of integration, right? So the region of the xy plane, and let's see if I can graph it here. Should be pretty easy. This is x equals y, or y equals x, right, to x equals 1. So x equals 1, let's say, is here. And we're going from y equals 0 all the way up to y equals 1. And that's up here as well. So it's this little triangle here, right? So switching the order should be pretty simple. We now want to do dy dx. So y goes from, let's see, x to 1. Right, y equals x. Wait, hang on. Y equals 0 to y equals x. Right, we're going up, not left. Right, so y equals 0 to y equals x. Sorry about that. And, oh, I know, that's why I got a little confused here. This should be x, dy dx, right? So yeah, x goes from 0 to 1 now. Okay. Yeah, let me fix that, right? So this is dy dx. So we switched the order of integration, and we had to adjust the limits of integration. And now we should be able to do this integral very easily. If it doesn't look easy, just keep in mind this is an integral with respect to y. E to the x squared is a constant in terms of y, right? So we're just integrating 1 dy, right? Which is just y. Evaluated between 0 and x. So it's just x minus 0, or x. Right. And now this is, well, I would claim trivial. At this point, you should know how to do this, right? It's just ordinary substitution. If u is x squared, du is 2x dx. So just multiply by 2, divide by 2, and we're going to get 1/2 the integral of e to the u du from, well, 0 to 1, right? 0 squared is 0, 1 squared is 1. So this is 1/2 e to the u evaluated between 0 and 1. So 1/2 of e minus 1/2 of e to the 0, which is 1. So e minus 1 over 2. Okay. So, yep, this had to be done by switching the order of integration. And if you notice in part B, it has to be done the exact same way. You're not going to be able to do it directly here, right? So let me just write down b very quickly. This is the integral from 0 to 1 of the integral from e to the y to e of x over log x dx dy. Okay, so yep, I have no idea how to evaluate this integral at all. So that tells me we're just going to have to switch the order of integration again, and we'll just do a usual graph here. So e to the y, x equals e to the y is just y equals log x. So that's going to look like this. Right. Y equals log x. And then x equals e is right around here. Right? And log of e is 1, so this is y equals 1. And then y goes from 0 to 1, so it's this little region in here. So that's my region of integration, right? We can call that R. And now we can switch the limits of integration, right? So we're still integrating x over log x, but now we're going to do it changing the order dy dx. So y goes from 0 to log x, and x goes from, remember, right, log of 1 is 0, so we're going from 1 to e here. 1 to e for x. Okay, so yep, because we're doing the integral with respect to y, x over log x is considered a constant. So once again, this inside integral here is trivial. It's just y. So when you evaluate this between 0 and log x, you just get a factor of log x, which is quite fortuitous because you're just going to cancel that pesky log x here. So now we're just going to integrate from 1 to e of x. So you know that's 1/2 x squared, evaluated between 1 and e. So e squared over 2 minus 1 squared over 2. So here we get e squared minus 1 over 2. And that's number 10, part B. Okay, number 11. We want to evaluate the double integral of e to the negative x squared minus y squared over the region D. So I know usually I use R here for region, but here D is the unit disk, so D could stand for disk, or it could stand for the domain, right? Because this is effectively, right, the domain of the region over which we're integrating here. But we'll go with disk. All right, so how can we do this? Well, with respect to x and y, do dy over dx, or dy then dx. So this is the unit disk, right? This is going to be y is equal to plus or minus the square root of 1 minus x squared. So we're going from the bottom half, negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then x just goes from negative 1 to 1. Right. On the other hand, you're going to see that's pretty difficult to evaluate this, this integral with respect to y. So, of course, this is a circular region, right? So we should probably use circular coordinates or polar coordinates. So that's the usual dr d theta, right? And, well, x squared plus y squared is r squared. So negative x squared minus y squared is just negative r squared, right? So the integrand here is just e to the negative r squared. R, of course, goes from 0 to 1 because it's the unit disk, radius 1. And theta, well, we want the entire disk, right? We want to go all the way around. So 0 to 2 pi. All right. Yeah, so there's no theta dependence here, so we can just do the d theta separately. And, okay, so this is not exactly trivial with respect to r. It does require a little mini substitution here. So u is negative r squared. Du is going to be negative 2r dr. So we need to multiply by negative 2 and divide by negative 2. Okay. So the first integral here from 0 to 2 pi of theta, that's just 2 pi. That's trivial. So let's see, we have the negative 1/2, and then we're going to integrate e to the u du. But if r is 0, u is 0. And if r is 1, u is negative 1. So this is going to be interesting. We're just going to get negative pi times the integral from 0 to negative 1 of e to the u du. So that's just e to the u evaluated between 0 and negative 1. So e to the negative 1 minus e to the 0 is going to be, let's see, so negative pi times 1 over e minus 1. And just so you know, this is a positive number. So this is positive pi times 1 minus 1 over e. Right? Or if you prefer, pi times e minus 1 over e. And that's the exact value. You're welcome to approximate it if you want, but I'm looking for the exact value here for number 11. Okay, number 12. We want to find the volume of the solid. Again, Q is just the symbol for a solid here, which lies below the graph of z equals x squared plus y squared. So that's just the usual paraboloid. Here's the positive z-axis. Oops. Z. So, yep, it'll look something like this. It's just the surface of revolution going around the z-axis, right? All right, close enough. So below that, right? So underneath that. So in fact, here's, let's say this is the projection underneath the surface, right? And above the region D, which is bounded by y equals x squared and x equals y squared. So that might look better in the xy plane. So this is y equals x squared. And then this is x equals y squared. So we're talking about this region in here. Trying to fill that in. Yep. So what would that look like over here? So something like this curve and this curve. Yeah. So just fill that in. So we're talking about this tiny little slice here. Going up to this surface here. So above that piece of the xy plane, but below the paraboloid. Okay, so what is the volume of that region Q? Okay, well, there's a couple ways of thinking about this, right? We can think of it as a triple integral integrating 1 dv. Right, so the region is just going to be, let's see, if we do dz, dy, dx, then, right, so these intersect at 1, 1 and 0, 0. So I hope I left enough space here, right? So y goes from x squared to square root of x. And x just goes from 0 to 1. And z, well, goes from the xy plane, which is z equals 0, 2, z is equal to x squared plus y squared. That's the paraboloid. Right? So that's one way to think of it. Or you can think of it as just a double integral of the region over the region R of the surface z, or maybe as a function of x and y, dy dx. And this is exactly what will happen when you evaluate this first integral. Right? You're just going to get x squared plus y squared, minus 0. And then just evaluate, or just take the integral of that with respect to y now. Okay, so doing that inside integral, we still have to do the integral from 0 to 1. We're just going to get x squared y plus 1/3 y cubed, and evaluate that between y equals x squared and y equals square root of x. These are y's, of course. So let's do the square root first. We get x squared square root of x plus 1/3 square root of x cubed is just x squared of x, right? And then minus, when you plug in x squared times x squared is x to the 4th, plus 1/3 times x squared cubed, which is x to the 6th. Okay, so at this point, this is a standard single integral. In fact, you're welcome to just plug this in your calculator. So let's say this will be x to the 5/2 plus 1/3 x to the 3/2 minus x to the 4th minus 1/3 x to the 6th. So working that out, you're going to get 2 over 7 x to the 7/2 plus 1/3 times 2 over 5. So that's what, 2 over 15? Do that quickly. X to the 5/2 minus 1/5 x to the 5 minus 1/3 times 1/7. So 1 over 21 x to the 7th. And you're really just plugging in 1. When you plug in 0, you just get 0. So this is 2 over 7 plus 2 over 15 minus 1 over 5. Oops. Minus 1 over 21. And I think that just works out to 6 over 35. So that is it's this double integral, it's this triple integral, and it represents the volume of this little slice of this region, this little purple slice here. So, yep, this is going to have volume, very small slice here, 6 over 35. Okay, that's number 12. All right, number 13. We want to evaluate this triple integral, right, over dv, over the region Q. We'll get to Q in a second. The integrand is 1 over x squared plus y squared plus z squared. Okay, so what is Q? Q is bounded by the surfaces x squared plus y squared plus z squared equals 1. So that's just the unit sphere. That's this in orange over here. Right? So that's the unit sphere. So between that and x squared plus y squared plus z squared equals 9, that's the sphere of radius 3. Right? So in between those. And also z equals the square root of 3x squared plus 3y squared. Okay, so what is that? If it's not familiar, let's see if we can simplify it. This is 3 times x squared plus y squared under the square root. So that's just the square root of 3r squared, or just r times the square root of 3. Remember, r is positive, right? So z over r is the square root of 3. So remember what z over r is. This is z, this is r, right? This is rho. So z over r is adjacent over opposite for this right triangle here. So I guess that's cotangent. So cotangent of phi is equal to square root of 3. Or if you prefer, tangent of phi is square root of 3 over 3. So I think that's just a 30-degree angle here. So this is just a cone, right? This is a cone where if this is the z-axis, you're just going out 30 degrees. Right? So essentially it's everything in between, right, these two spheres, but with inside the cone here. So horrible graph, but that's the idea. So that's the region Q over which we want to integrate. Okay, so I hope you're not even contemplating doing this in rectangular coordinates. These are spheres after all, so I would use spherical coordinates. So that's rho squared sine phi, d rho, d phi, d theta. Theta, of course, just goes from 0 to 2 pi. You know what, let me, so I messed up the integrals here. Let me have a little more space. Just clean that up. Okay, so this is the theta integral. We're going from 0 to 2 pi. This is the phi integral. We're going from 0 to, yep, that's what this was about, right? 30 degrees, or pi over 6 radians. And then rho just goes from 1 to 3, right? The inside sphere here has radius 1. The outside sphere has radius 3. So we're going from 1 to 3 for rho. Right? It's everything in between. Oh, and the integrand is 1 over rho squared. Right? Which is convenient because that's going to cancel with the rho squared from the Jacobian, right? So, yep. So let's see. The outside integral from 0 to 2 pi d theta. The inside integral from 0 to pi over 6. And we're just integrating sine phi, d phi. And then the rho integral is from 1 to 3 of just 1 d rho. Right? So, yep. The d theta integral just gives you the usual 2 pi. This, when you integrate sine, you get negative cosine, right? Right. So negative cosine from 0 to pi over 6, or cosine from pi over 6 to 0. Just flip it. And then you just get rho evaluated between 1 and 3. Okay. So you're going to get 2 pi times, the cosine of 0 is 1. The cosine of pi over 6 is square root of 3 over 2. And then this is just 3 minus 1, right? Or just 2. So 2 times 2 pi is 4 pi times 1 minus square root of 3 over 2. And that does it, right? That's the value of this triple integral, right? Be careful, it's not the volume of this region because, right, we didn't integrate 1. We integrated 1 over rho squared. We integrated this function. So think about this as, you know, your density function. If this represents the density, what we just calculated is the total mass of that object. Okay, so that's sort of the interpretation here, right? We're integrating 1 over rho squared. So, all right, either way, this is the value of that triple integral. All right, moving on to number 14. We want to calculate the work done by the force F, and this is a vector, right? So this is a vector field now. We're entering, you know, chapter 15 territory here. This is the vector field xy times I plus x squared times j. So I don't know what the z is doing here. This is a vector field in the plane. So if you want, you can say plus 0k, but it doesn't depend on z at all. So, right, in fact, the curve takes place in a plane, so we don't need the k component at all here. So this is, right, so we're moving along a curve given parametrically by this function. So we have sine of t times I plus 1 plus t times j. So this is a curve in the plane, right? And t goes from 0 to pi. Okay. So, right, so what does it mean to calculate the work? Right. Again, this is a physics concept, but the idea is it's just the line integral over this curve of f dot dr. It's the line integral. Right? We're just calculating the line integral. Okay. And so this is done the usual way. What's dr? Well, the derivative of r, right, or r prime if you will, is just going to be cosine of t and then 0 plus 1, right? So dr then, if you just multiply by dt, it's this vector here, cosine t1 times dt. Okay. And of course f is a function of x and y, right? It's just xy x squared. But in terms of t now, remember x is sine of t and y is 1 plus t. Right? So sine of t times 1 plus t. And then x squared is just sine squared. Okay. So I'm just substituting for x and y these components here, right? Okay, now we take the dot product, right? So f dot dr is going to be the dot product of these two vectors. Let me put the 1 plus t first. 1 plus t times sine t, and then sine squared t, dot product with cosine of t1 dt, right? So that's just going to be 1 plus t times sine t times cosine t, oops, sorry, not comma, but plus sine squared t times 1, or just sine squared t. And this will be all times dt. So that's the function we're integrating, right? We're just integrating this rather horrible function here, 1 plus t times sine t cosine t plus sine squared t. So here you're going to have to start remembering some of your Calc 2. So this, we might have to do an integration by parts here, or some sort of reduction formula for the sine squared. Now, what are the bounds on t? Well, they're given, right? These are the limits for t. T goes from 0 to pi. So we're integrating from 0 to pi. Okay. So, yeah, at this stage, you do your integration by parts. In fact, there's a formula on your formula sheet for the integral of sine squared. So you just work all this out. And you should get, let's see, I think it's 1/2 t minus 1/8 sine of 2t minus 1/2 cosine squared t minus 1/4 t cosine of 2t. And then you just plug in the 0 in the pi. So I think we're just going to get, let's see, pi over 2 minus sine of 2 pi is 0. Cosine of pi is -1, but when you square it, you get +1. So that's going to be plus 1/2. Oh, no, minus 1/2. Right? Minus 1/2. And then, let's see, minus 1/4 times pi. And then cosine of 2 pi is 1. Okay. And then when you plug in 0, you just get 0 minus 0. Cosine of 0 is 1, so minus 1/2. And then 1/4 times 0 is 0. So I think we're just going to get pi over 2 minus 1/2 plus 1/2 minus pi over 4. So I think that's just pi over 4. So that's how much work is done to move an object along that curve, right? It's pi over 4. So yeah, I skipped a few steps here and right doing the integration by parts and all that stuff, but I think you can handle that as long as you remember your Calc 2 methods. And yeah, so I think this video has gone on long enough. I'm going to stop here and then continue. We'll do part 2 for the rest of it.